Hi, this talk is titled Production Ready Server Side WebAssembly The Challenging Parts. My name is Saul and I work in developer experience and WebAssembly at Shopify. On June 3rd, 1973, spectators gathered at Le Bourget Airport for the Paris Air Show. People gathered at the airport to witness the flawless presentation of the Concorde. This aircraft represented a breakthrough in aviation. It was responsible for enabling commercial supersonic transport. Creating the Concorde was an engineering challenge. Fast forward 3 years, in 1976, the Concorde started officially flying between New York City and Paris at supersonic speeds. A, a round trip was tagged at 12,000 US dollars. By the wealthy, this was considered a once in a lifetime luxurious experience. This was 30 times the price of a normal ticket. However, the Concorde lasted only a couple of decades. And you may ask yourself why. Don't breakthroughs get better and cheaper with time? Well, to explore why, let's take a look at a couple of quotes. The first one says, the idea of Concorde was bigger than Concorde itself. This probably means that the actual implementation of the Concorde was not as good as the idea itself. The second quote says, the idea was perhaps more important than the actual experience, which was cramped and expensive. This quote hints that even though the Concorde was feasible, it was probably not sustainable. We are a WebAssembly Summit. Why are we talking about airplanes? I wanted to share the story of the Concorde not because WebAssembly has anything to do with supersonic tech, but because I think it's inspirational to highlight what they have in common in terms of challenges. It all boils down to engineering innovation. Both of these technologies represent a breakthrough in an industry. Many of the foundations of aviation had to be revisited in order to make the Concorde possible. So we are going full circle with WebAssembly too. Many of the ideas of WebAssembly have had already existed, but WebAssembly is improving the foundations of the industry to make it possible. Throughout the years, Concorde's challenges as a technology were not strictly related to its engineering internals, not even related to the supersonic transport. um, Throughout the years, Concorde's challenges as a technology were not strictly related to its engineering internals, not even to the idea of commercial supersonic transport. All the challenges were mostly related to the concerns around its usability and how it affected its ecosystem. In this talk, we'll explore how WebAssembly's challenges and success factors are, in a conceptual level, similar to those of the Concords. The takeaway of this analogy is to learn that more often than not, engineering innovation is highly dependent on how accessible, usable, and backwards compatible it is. In that sense, engineering innovation should strive for progress and not for perfection. Enough about planes, let's talk shop. Before talking about WebAssembly, it's important to make sure that everyone has some level of understanding of Shopify's use case for WebAssembly. This is a small parenthesis to talk about extensibility at Shopify. There's a full talk on the topic, by the way, by Mitch Dickinson. Mitch and I work on the same team at Shopify, and if you haven't watched it, I highly recommend you do to go deeper on our use case. The talk is titled Making Commerce Extensible with WebAssembly. Shopify is a multi-tenant software as a service commerce platform, and we want to make commerce better for everyone. And when we say everyone, we mean everyone. If you haven't heard about Shopify, you might have heard about some of our most successful merchants, like Gymshark and Allbirds. However, we don't focus on how big or small a merchant is. We want to make commerce better for merchants that are just starting as well as for those that are already well established. This means a couple of things. The first one is that we are transitioning from being a product to being a platform that has extensibility as a first class citizen. This means that instead of worrying of filling all the possible gaps in terms of business use cases that we support out of the box, we have adopted an extensible platform approach in which any business use case can be fulfilled by extending the platform itself. The second point is that extensibility is critical to develop highly specialized solutions for those merchants that need them. Those solutions can be developed by the merchant. Think about a merchant that's building an engineering team to build custom solutions, or by partners. Partners will develop apps that will be later installed by merchants to fulfill those use cases. Extensibility is not a one size fits all paradigm. So let's dive a bit deeper on the principle of extensibility as a first class citizen. There are several things to consider here. The first one is that Shopify already offers a variety of extensibility mechanisms, like GraphQL APIs, Liquid APIs, and webhooks. Most of the time, these mechanisms work for most use cases. Like, for example, a partner can use a GraphQL API to build an app that will be installed by a merchant, and this app will fulfill a use case that Shopify doesn't provide out of the box. One of the main examples of this is enabling subscriptions. Partners can use the GraphQL APIs and Liquid APIs to ensure a coherent subscriptions experience. Now, checkout is critical to Shopify. There is no commerce without checkout, and as so, the checkout needs to be resilient, secure, fast, and customizable. Checkout is a performance-sensitive context, and the standard mechanisms are harder to fit for many reasons, but one of them being latency. It's very expensive and very risky to make external calls from a checkout flow. What if the app is down, or what if the request takes too long, for example? Another reason is merchant use cases. Even if we could fit any of the standard mechanisms, it would be very difficult to satisfy each and every one of the merchant's needs without sacrificing the composability of the APIs themselves. Here's where a more granular extension mechanism comes into play: Shopify scripts. It will be referred to as scripts or the scripts platform for the rest of the presentation. WebAssembly backs the new scripts platform to enable synchronous business logic customizations to our commerce monolith through third-party code. We haven't released this yet, but we are getting ready to do so. Once we do, potentially several thousands of partners will be exposed to WebAssembly. Developers will be writing customization code that will be used by potentially more than 1 million merchants. We are not taking this statement lightly. Exposing developers to WebAssembly means two main things. The first one is that this use case has the potential to increase WebAssembly's adoption. And the second one is, as a consequence of the first point, we're betting on WebAssembly to empower developers to get things done and not to get in their way, looking for the best developer experience possible. So before taking a look at how our platform looks, let's inspect why we have chosen WebAssembly. The first thing is that customizations that we're intending to write in WebAssembly are synchronous. They run on the server, but they are surfaced to the buyer in several forms. We'll see an example later on. In e-commerce, every second counts, and even the smallest delays can cause drops in conversion. So this means that customizations need to be seamless and very fast. Now, the second point is that customizations are by definition untrusted code. So we need to run such customizations in a safe way. Our needs for this platform are directly proportional to WebAssembly's current features. This is everything that works. Let's assume that I'm a partner is working on an app to filter out payment options at checkout. The filtering part will be done through a script. In this case, we want to filter out a payment option called Wholesale Gateway. We only want to show the Wholesale Gateway to wholesale customers. So with the Shopify CLI, we create a script. We enter the name of the script, and we choose the payment filter as the API that we want to use to create this script. Then the script gets created, and we change directories to WebAssembly Summit. Once we do that, if we inspect the project, we can see the following structure. We have a test suite powered by Aspect, we have source files written in assembly script, and we have other configuration files. The logic of the script lives in src/script.ts, and it looks like this. We'll break this down a bit in the next slides. In the first line, there are a couple of things to note. The APIs are distributed as NPM packages, which partners can use to write their scripts against. In this example, the partners get access to checkout and payment method APIs. The next important part to note is the signature of the payment filter handler. It has an input argument that represents a checkout, which has all the public checkout attributes. The second argument is a configuration object. You can think of a configuration of a simple key value store. And then the return type of the function is an array of payment methods that will be validated and applied to the current checkout once the execution of the module finishes. Now, this is the main logic of the script. Our intention is to make APIs as declarative as possible. Note that we create a payment method filter class to which we pass the input and the configuration. This is done mainly as a workaround since AssemblyScript doesn't support closures. In the body of the filter callback, we perform the filtering logic. Once we are done, we request the filter methods from the filter class. Now, once the developer is happy with the changes and assuming that they have written unit tests, they can push their script to production. There is some deploy magic going behind the scenes that is not relevant for this talk. What is relevant, though, is what happens with the module itself. The first thing is that it gets deployed to our execution engine, which is written in Rust and uses a reactor model through Tokio. Then the module gets compiled using the Lucet ahead of time compiler, and then a shared object is generated and is stored for later use. Now, once the merchant has installed the app that has a payment script associated, all the traffic served at checkout for that store will start executing the logic to filter out the payment methods. It's important to note that while the execution phase is happening, the checkout is still loading. So that means that we haven't presented the payment methods to the buyer. And here's where the efficient characteristic of WebAssembly comes into play. Up until this point, the merchant is happy, the developer is happy, and the buyer is happy. We can say that WebAssembly has fulfilled its promises in terms of performance and safety. But what happens after? Someone could say, okay, let's call it a day. I would say not so fast. Let's rewind and dive a bit deeper on each of these areas and zoom on the immediately challenging pieces. But first, let's make sense of the Concorde analogy. Before, I mentioned that many of the Concorde's challenges were not strictly related to enabling commercial supersonic transport. Many also believe that the Concorde was retired due to the unfortunate Air France crash in 2000. Digging a bit deeper in its history, we can see that there are other root factors. The first one is the cost of maintenance. The Concorde ended up in a niche market of fast transatlantic flights, not necessarily by choice, but because supersonic booms caused damages and affected people. This affected its wider adoption, making tickets expensive and the cost of maintenance very high for airlines. The second factor was environmental issues. Because of its supersonic speed, the Concorde had to fly at very high altitude. This ended up having negative effects on the ozone layer. So at this point, what is the real cost of commercial supersonic transport? Concorde's failure is directly proportional to how well it integrated with its environment. This technology was disruptive, but it was not totally backwards compatible. It affected the adopters and the final users. The same could be true for WebAssembly. Let's see how these challenges relate to the current state of WebAssembly. The first challenging piece is writing programs. Given the compilation target nature of WebAssembly, it's crucial that all the programming languages widely used today can target WebAssembly efficiently. Let's go back to the payment filter example. Let's assume that I'm a developer trying to get started with Shopify scripts, but I'm only proficient in JavaScript. So what are my options? There are several options to write these programs today. These are a few, but are all of them suitable for all use cases? One would expect that with WebAssembly's polyglot characteristics, this would be true. But the reality is that there is still work ahead of us in this area. Each language has a fairly unique method to compile its programs to WebAssembly. This is greatly due to two main things. The first one is each language unique characteristics, and the second one, the lack of finalized standards to perform operations like garbage collection. The compilation phase then results in modules that are not totally uniform, and they will vary depending on the compilation toolchain, making them not suitable for all use cases. For example, they could have a negative impact if you need to embed an entire language runtime, which would be the case if we wanted to compile JavaScript to WebAssembly today, for example. But despite all that, programming languages are the first element to consider when trying to be backwards compatible, as they represent the main tool to interact with WebAssembly. So enabling support in widely used programming languages is one of the best ways to interact with the environment surrounding it. Examples of initiatives like this are SwiftWasm, Go, and TinyGo. This approach makes WebAssembly more reachable and less costly to adopt. Now, creating new programming languages is a heavy task on its own, but creating the ecosystem for that language is as hard or even harder than creating the language itself. This is costly not only for companies adopting WebAssembly, but for developers too, as they need to learn new tools. There are several proposals that are critical for the success of this and many other similar projects, like garbage collection and interface types. In the early days, when WebAssembly was associated only with the web, WebAssembly was seen as a performance-only technology, and thus that it was going to be dominated by languages that prioritize performance, like Rust, C, or C++. There is nothing wrong with these languages. They are exciting projects, especially Rust. But with the growth of WebAssembly on the server, the rules have changed. WebAssembly is not opt-in anymore. WebAssembly is the actual platform. Developers that host scripts or apps in platforms that run WebAssembly on the server, they probably want performance, but they also want to get their things done, ideally without having to learn new languages just because the compilation target changed. The combination of WebAssembly use cases on the server combined with the popularity of high-level programming languages like Python, Ruby, and JavaScript, and all that added to enabling these languages to compile to WebAssembly is a recipe for great developer experience and a potential road for greater adoption. The next challenging piece is understanding programs. No developer writes perfect code. In fact, in order to be able to write good code, developers need to understand how their programs behave in the execution environment. Let's go back to the payment filter example for a moment, and let's assume that I'm a partner developer that pushes an update to their script. The update is successfully deployed, but it contains a division by zero bug that was not caught by unit tests. The checkout starts serving traffic with the updated script. Then the scripts start failing. The developer only sees the following error in their partner dashboard. They have no idea where in the original source code the error is coming from, and they have to debug the script locally, relying on logging a unit test to understand what happened. Added to that, the error might not be strictly related to their implementation. What if the variable that caused the division by zero is coming from the production system? So there are a couple of challenges here, and there are a couple of avenues to improve the experience today. The first one will be source maps. First, this will only be available in debug builds, and they have code size implications. And storing them separately is not trivial either. And the final flaw of source maps is that they were designed mostly for JavaScript, so the experience is not very great. The next option is a debug protocol like Dwarf. Again, this is mostly available in debug builds. It also has code size implications, and it's not fully supported by runtimes and by languages. And again, it has the same challenge as source maps, where storing them separately is not trivial. It's crucial for developers to understand how their modules behave in production. This is especially relevant for Shopify's use case, given that a bad script might cause unexpected behaviors at checkout. For this, currently we have workarounds that we are considering at Shopify. The first one is local tooling for integration testing. This gives the developer at least an extra layer of confidence. And then the second workaround is making sure that the developer is logging the rough edges of their script so that they can understand what's happening in production. In an ideal world, though, this is what should happen. When a faulty script is deployed and errors start happening, developers should be able to diagnose where the error is coming from in the original source code. And there are two main things that would help substantially to improve the experience in this area. The first one is the exception handling proposal, and the second one is standardizing a debug format like Dwarf in runtimes and language toolchains. Now, the third challenging part is guest-host communication. It's great that all of WebAssembly's features are designed with security and performance in mind. When applying WebAssembly to a real-world use case, modules needs to be secure, but also fast. But also they need to do meaningful things. And doing meaningful things involves communicating with the host, receiving some input and returning some output. So let's assume that I'm a Shopify developer working on the scripts team, and I'm trying to enable APIs and communication between guest and host. What are my options? Well, your options can be any of direct allocation relying on the guest's memory module. This would work, but your system will be coupled to a memory representation of your guest language, making it harder to add new languages in the future. You can use JSON, but depending on your input, the encoding decoding can be very slow. And then you can use other binary formats like MessagePack. All these methods work, but they require a non-trivial amount of glue code. And depending on the ecosystem of the guest language, a serialization library may or may not be available. If it's not available or if it's not mature enough, this exponentially increases the amount of glue code. Instead, having a standard way of representing complex types between the guest and the host should be the ideal approach. This is what the interface types proposal is all about, and that's why it's so important. It will unlock standards to perform operations like this one. Let's revisit the analogy of the Concorde one last time. This phrase caught my attention. Breakthroughs can fall short without a disaster. In the end, it was proven that a disaster was not needed for a disruptive technology like the Concorde to become a museum exhibit. There is only one condition to prevent this from happening to WebAssembly, and it is continue making it affordable, usable, and backwards compatible so that it can integrate with the existing ecosystem gracefully. I have several closing thoughts to complement this phrase. And the first one is around tools and languages. I believe that tools and languages should empower developers to get their jobs done. There should always be a balance between optimizations and usability. Usability is probably the right bet today. WebAssembly is only getting better and faster every day, anyways. So it's probable that the majority of developers using your tool are not concerned with the internals. Your tool or language might mean a developer's first interaction with WebAssembly, so there is a huge responsibility there. The next line of thoughts are for people working on this. The next line of thoughts are for people working on the spec. I would like to call out that prioritizing proposals that have a direct impact on the perception of WebAssembly and that will make the implementer's life easier is probably the right bet. Like prioritizing proposals like garbage collection, interface types, and exception handling. And the last thought is keeping in mind that WebAssembly is moving from being an opt-in technology to being the actual platform for very complex server-side use cases. And that's it for me. Thanks.